So this is where we left off in Lecture 13. Wanted you to recognize you put them in separate orbitals first. That's part of Hund's rule. And the other part is you want them to point all in the same direction because of resonance. Okay. So resonance is something that shows up time and again in quantum mechanics. If you have two quantum mechanical objects that are exactly the same, then you don't know whether this is A and B or B and A. Okay, electron Alice and electron Bob. They can swap places perfectly easily, and they do. Okay. So that's a thing called resonance. These guys sort of see each other across space, and they say, "Hey, you're just like me. We're spin buddies." Okay, and that lowers their energy. It makes them more stable. Okay. Remember, if you have something on a high place, a ball or something, then it can fall. But if it's already on the ground, it can't fall. It's more stable. Right? The same is true for electrons. So the fact that they resonate, they gain that resonance stability, and that lowers their energy. That makes them more stable. So whenever you see opportunities for resonance, you grab a hold of that with both hands and recognize that resonance makes things more stable. Okay. So looking again at our periodic table, here is our periodic table. Let's start with chromium first. Chromium here is element number 24. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4. Okay. So all of its sublevels prior to the final sublevel are going to be full. So that's kind of a shortcut. Okay. Next we look at copper. Copper is also here in the fourth row, and it's also in the transition metals. So we're looking at 3D. So 1s2, 2s2, 2p6, 3s2, 4p6, 4s2, 3p6, 4s2, I'll assume I got that right, are all going to be full. And then it's 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we look at silver. Silver is down here. It's element number 47. So all the sublevels are going to be full before you get to 5s2, 4d something. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now is the time where I get mean, because I have to point out that reality is mean and wants you to suffer. Silver, symbol Ag, is one of the exceptions to orbital filling, okay, to electron configurations. You expect 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. Okay. But it is an exception because instead, these two are different. It's 5s1, 4d10. When you get toward the bottom of the periodic table, when you're starting getting low, down here, okay, the energy levels and sublevels are all getting closer together. You may not recall, but energy goes as 1 over n squared. Okay. So the difference between, for energy level 1, okay, it's proportional. For energy level 1, that means it's proportional to 1 over 1 squared equals 1. for energy level, okay, for n equals 1. For energy level 2, that's 1 over 2 squared equals 1/4. For energy level 3, that's 1 over 3 squared equals 1/9. Okay. For n equals 4, 1 over 4 squared equals 1 over 16. Then you have 1/25, 1 over 36, 1 over 49. We're looking at smaller and smaller fractions. Okay. So they're getting closer and closer together. Okay. The difference from here to here is 0.75. Then from 2 to 3, it's 0.25 minus 0.11111, so 0.14-ish. And then from 1/9 to 1/16, it's even smaller, then smaller, then smaller. Okay. So the energy levels are getting closer and closer and closer together. Okay. So drawing them in their proper way, 1, 2, 3. Well, let's make it so that they can fit on the screen. Well, actually, you might recall, you can actually see it in the Balmer series, or the Lyman series, or so on. Okay, remember the lines of hydrogen, Balmer series. Okay. Images. Let's hope there's one really handy. Yes, there we go. Okay, so energy level 1, 2, 3, 4, 5, and 6. They're starting to get really crowded up here toward the top. So what happens for silver is, ignoring the rest, you have 5s. The 5s orbital has 2 electrons in it. And then here's 4d with 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now this energy level, or the difference right there between 5s and 4d is tiny. It's a small difference. Okay. So here you have this electron, this electron, this electron, and this electron are all exactly the same. So that's a lot of resonance. Okay. Whereas this one, and this one, and this one are all exactly the same, so there's resonance there. Okay. But it is less resonance. If you take this electron and bring it up here, that would get you that. And you would have two things going on. The energy going from 5s to 4d. Okay, that's an increase in energy. And then you have the energy of resonance, because now this guy is just like this, and this, and this, and this. No resonance here. In the s orbital. Okay, the s orbital is always all by itself, so there's no resonance there. Okay, there can never be resonance in an s orbital or an s sublevel. I often get those two mixed up because the s sublevel is a single orbital. Okay, so for silver, the question is, does resonance make up for having to bump it up a sublevel? And the answer is yes. So silver is actually 5s, 1, 4d, 10. 10. Okay. The resonance makes silver happier like that. And you see that in the way silver behaves, because silver, when it forms an ion, when it does a chemical reaction, it only ever forms a 1+ ion, okay, because it's only losing one electron. These d electrons are always way too happy to react. So that is an important exception that you need to know. That's why I included it here. Oh dear, there's a typo. 4p6. The 6 should be a superscript. All right. So Orbital filling is something you are going to have to know. You need to be able to just write out the list of all the electrons in an element. Okay. Other exceptions you need to know are copper is sometimes an exception, okay, because it can form either a 1 plus or 2 plus ion. We're looking at lower energy levels, so the difference between 4s and 3d is greater. So the gain you get from increased resonance doesn't quite make up for the bump from 4s to 3d. So copper sometimes forms a 1 plus ion because it's sometimes like this, but most of the time it forms a 2 plus ion. Because it doesn't always bump that s electron up into the 3d orbital. Okay. Whereas for chromium, if you look back at the periodic table, okay, chromium is 4d4. So we clear off this. 3d. 1, 2, 3, 4, and it has 4s, 1 and 2. It can bump this electron up to here, and thus get extra resonance, making it 4s1, 3d5. Again, because the difference between the 4s and the 3d is slightly larger, chromium doesn't always do that. But for silver is the one I absolutely expect you to know, because it always does that. But later on, the fact that copper and chromium can do that, but don't always do that, will be helpful in understanding chemical behavior. Okay. So now let's talk about the difference between core and valence electrons. Okay. The outermost shell of electrons are the only ones that participate in chemistry. Okay? So, looking back at our periodic table, carbon has 1s2, 2s2, 2p2. Okay, the electrons in the second energy level are the only ones that participate in bonding, or in chemistry of any kind. Okay? Those two 1s electrons, they don't participate. Because they are much lower in energy, they're far more stable, they're far happier than the second energy level electrons. Okay? The other reason is because when you actually look at the atom, okay, here you have your nucleus with its protons and neutrons. Here you have those two 1s electrons, okay. They are right close next to the orbital. Then you have the 2s and 2p electrons. 2s, 2p electrons. And they're further away. Okay, so these, okay, let's just go ahead. 1s, 2s, 2p. Not only are these guys closer and more tightly bound to the nucleus, but they also act as a shield. They are in between the nucleus and the outermost energy level. Okay, so these guys, they don't feel the nucleus quite as strongly. I'll qualify that. They don't feel it as much. It's not that they don't feel it at all, it's that they don't feel it as much. Okay. So, core electrons act as a shield, and they just sit there. They don't participate in chemistry because the valence are in between them and the rest of the world, and the valence electrons don't feel the nucleus quite as much because the core electrons are in between the valence and the nucleus. So that allows us to abbreviate our electron configurations. And we're at 15 minutes now, so I'm going to go ahead and cut it off there. And we'll pick this up in lecture 14.